So we'll move to a slightly different track now, right? So we have kind of seen, right, that you can use Hoare logic to prove the validity of a Hoare triple using the inference rules, right? We will see another procedure um, again involving Hoare logic to prove the validity of a Hoare triple, but this time we are going to generate a formula, right? So we are going to generate what's called this verification condition, and the goal is that at the end of the day, right, we want to reduce the verification problem to the validity problem in FOL. So using this verification condition generation, we will generate one big FOL formula which we can just pass to an SMT solver, right? And if the solver says the formula is valid, then the Hoare triple is valid, right? So this formula we will generate using the inference rules for Hoare logic, right? So let's see how to do that systematically. Okay. So we have already seen that the weakest precondition operator, right, can be used to prove Hoare triples. So if you want to show that the Hoare triple PCQ is valid, then you need to show that this particular Hoare triple is true, right, which is P implies WP of Q comma C. So this is the basis of what we will do, right. So we are going to use the weakest precondition operator, and we have seen some of the advantages of the weakest precondition operator, right, in the sense that for assignment statements, right, in order to find the weakest precondition of an assignment statement, you just need to do a syntactic manipulation, right. So you just need to syntactically manipulate the formula, right, where you just replace, right. So if you have something like x colon equal to E, and if you find the weakest, if you want to find the weakest precondition for some formula Q, then this is the same formula Q except that E replaces x, right? So this is an advantage of weakest precondition, but WP fails when you have loops, right. But now we have an answer to that, which is loop invariants. So we have a program with loop invariants. How to use that in the weakest precondition procedure, right? So finding exact WP for loops is hard. So what we will do is we will instead use the loop invariant itself as an approximate weakest precondition, right? So given an annotated while loop, right? So here this while loop is annotated by a loop invariant I. We are going to say that the approximate weakest precondition of Q and this while loop is just equal to the annotated loop invariant I itself, right? So what this means is that, again, right, if you recall weakest precondition, right, what it says is, if you execute the while loop, right, beginning from any state which satisfies I, and if the execution terminates, then it should be guaranteed to end up in the state Q, right? So if this is the case, then only then we can say that I is the weakest precondition, right? So which means that this in general you cannot always say, right? So you need to prove some side conditions, right, which is that if you execute this while loop, right, beginning from any state in I, and if the loop terminates, it should be guaranteed to end in the state Q, right? So we know that this while loop is going to repeatedly execute the body, right? So essentially we need to show that if you execute the body of the loop, right, then you remain in the state I, right? So which means I is actually an inductive loop invariant. So this is the condition for inductive loop invariant, which is that this Hoare triple should be valid, right? That if you execute the body of the loop in a state which satisfies I and F, then you should continue to remain in, or the state should continue to satisfy the formula I, right, after executing the body of the loop. And finally, when the loop terminates, right, so the loop will terminate if the loop conditional is not satisfied. So remember, you have always ensured that you are in the in a set of states which is which obey the formula I, right. So when the loop terminates, you will not satisfy the loop conditional. So I and not F should imply Q. So you start the loop in a state which satisfies I, you execute arbitrary number of iterations, right, of the body of the loop, always making sure that you continue to remain in a set of states which satisfy I, and finally when you exit out of the loop, right, which means that the loop condition is not satisfied, then you should be in a state which also satisfies Q, right. So this will guarantee that any execution of this while loop beginning from a state in I if the execution terminates, it's going to end up in a state in Q, which is the exact condition that we need for I to be in the weakest precondition, right. So we need to show that these two side conditions hold, right. So if these two side conditions hold, then we can say that I will be an approximate weakest precondition, right, in the sense that executing the while loop beginning from a state in I is guaranteed to end up in a state in Q. Okay. So in fact, I is actually a fixed point of this function, right. So recall that when we defined the weakest precondition for while loops, right, then we had come up with this particular function, right, and we said that any fixed point of this function is actually or rather the greatest fixed point of this function, right, would be the weakest precondition, right. So I is actually a fixed point, but it's not the greatest fixed point, right. So WP was defined to be the greatest fixed point of this function, right, which is the same function, this f, right, f of f prime, and I is actually a fixed point of this function. Right? So this also you can separately show, right, that I is actually a fixed point of this function, need not necessarily be the greatest fixed point. So since it is not the greatest fixed point, right, we have changed this WP to AWP, right, because I is not the weakest precondition, right. So it's the approximate weakest precondition. So let's try to formalize this difference, right, between approximate weakest precondition and weakest precondition, right. So what is the difference between them? So we will first formally define what is this AWP. So AWP is just defined to be this set of states, right. So AWP, just like WP, is a predicate transformer, right. So again, it takes as input a set of states Q and the program C, right. And what we want to say is that if you start from any state that is in AWP Q comma C, so if you start from any state sigma that is in AWP Q comma C, and if you execute the program C, and if the execution terminates in a state sigma prime, then that state sigma prime is guaranteed to be in Q, right. So this is the definition of AWP, right, which is that it is a set of states such that if you start the execution of the program in any state which is in AWP, and if the execution terminates, then you are guaranteed to end up in a state which is in Q. So as a homework, right, you can try to show that if you define the approximate weakest precondition, right, for the while loop to be equal to the annotated loop invariant, and if the side conditions are satisfied, right, so we saw two side conditions in the last slide. So if both those side conditions are satisfied, then indeed I is an approximate weakest precondition, right, in the sense that I will actually satisfy this particular formula, right. So we kind of argued about this informally, right, on the last slide, but you can also formally show, right, that this is true. So what is the relationship between AWP and WP, right? So if you recall, WP was also defined in a similar fashion, right. So WP Q comma C was defined to be this set of states such that if you execute C beginning from sigma, and if the execution terminates, you are guaranteed to end up in a state which is in Q, right. But the difference, as you can see, right, is that for any state in AWP, right, we are only saying that this is true, but WP encompasses all such states, right. So if you take any state sigma, right, which is in AWP Q comma C, then that state is guaranteed to be present in WP as well, right. But WP is the weakest precondition, right, which means that it is the largest possible such set of states, right. So all such states may not be present in AWP, right. So if you take a state which is in WP Q comma C, then it need not be present in AWP Q comma C, right. So AWP Q comma C is essentially a subset of WP Q comma C, right. So recall that we had seen this weakest, right. So weakest in this particular terminology, right, always means the greatest set, right. So weakest precondition is the greatest set of states, right, such that if you start the program in any of those states, and if the program terminates, you are guaranteed to end up in the target state, right. While all we can say about AWP is that it is a subset of WP, right. So if you, again, in terms of Venn diagram, right, you have WP Q comma C, which is a bigger state than AWP Q comma C, right. So any state that is in AWP Q comma C is guaranteed to be present in WP Q comma C, but the vice versa is not true, right. So in fact, that's why we say that I is an approximate weakest precondition, right? Because it's based on what is there in the program, right? So it's an annotated loop invariant, so it need not encompass all possible states, right, which are present in the weakest precondition. Right? So this is the relationship between AWPQ comma C and WPQ comma C. So once we have this AWPQ comma C, we can then use this AWP for verifying the validity of O triple. Right? So recall, right, that in order to prove that PCQ is valid, so we had said that if you take this formula, right, so weakest precondition of Q comma C, right, and then if you show that P implies weakest precondition of Q comma C, right, then this 4 triple PCQ is valid, right. So if this formula is valid, then the whole triple is also valid. Now instead of using WP, all we will do is we will use AWP instead, right. So if the formula P implies AWP Q comma C is valid, then the whole triple PCQ is also valid. And what is the advantage that we get out of doing this? So the advantage is that if your program C contains while loops, then I can just use the annotated loop invariant for AWP, right. So this gives me a procedure, right, to actually get the approximate weakest precondition. So for every other program statement except the while loop, I already know how to compute the AWP, right, which will be the same as WP, and for while loop I am going to use the annotated loop invariant. So using that I can construct this formula, and then once I construct this formula, I can just give off this formula to a SAT solver, right, and if the SAT solver says that this formula is valid, then the O triple is also valid. Okay. So in order to illustrate this relationship between AWP and WP, right, let's look at a very simple example, right. So let's consider this particular example, right. So here I am asking, right, what is the approximate weakest precondition for, so this is the target set of states, right, Q, which is I is greater than or equal to 0, and this is my while loop, right. So it says while I is less than n, do I equal to I plus 1, okay, and my annotated loop invariant is I is greater than or equal to 0, okay. So whenever you have a while loop, right, with an annotated loop invariant, the approximate weakest precondition is just blindly equal to the annotated loop invariant itself, right. So it's just I is greater than or equal to 0, and of course you can also show that the side conditions also hold, right. So the side conditions here meaning that if you have I is greater than or equal to 0 and I is less than n, and if you execute the body of the loop, right, which is I equal to I plus 1, you should be able to show that I is greater than or equal to 0, right. So this is this I and F Ci, and I and not of F, right, which is I is greater than or equal to 0 and I is greater than or equal to n, should imply I is greater than or equal to 0, right. So I and not F should imply the target, right, which is Q, which is I is greater than or equal to 0. So in fact both of these conditions are true, right, in the sense that this whole triple is valid and this formula is also valid, right. So therefore the approximate weakest precondition is going to be just I is greater than or equal to 0. But what is the weakest precondition for the same set of states, right. So what are all the set of states that I can start from, such that if I execute this loop, I am guaranteed to be in a state where, so and if the loop terminates, I am guaranteed to be in a state where I is greater than or equal to 0. So in fact, so if you start in a state where I is greater than or equal to 0, right, so if you start the loop in a state where I is greater than or equal to 0, then if you execute any iteration of this loop body, right, you are always going to increment I by 1. So I will continue to remain greater than or equal to 0, right. So I is greater than or equal to 0 is definitely part of the weakest precondition, but is it the complete set, right. So are there any other states, right, from which I can start from, such that when the loop body terminates, the value of I will be greater than or equal to 0, right. So in fact, as you can see, right, that even if I start in a state where I is less than 0, as long as value of I is less than n, this loop body is going to execute, right. So if I can make sure, right, so when will this loop terminate, right. So this loop will terminate when I is equal to n. If I can make sure that the value of n is greater than or equal to 0, right, then no matter what the value of I is at the beginning of the loop, after the entire loop terminates, the value of I will be equal to n, which means that it will be also be greater than or equal to 0, right. So, in fact, the approximate weakest precondition of this is n is greater than or equal to 0 or I is greater than or equal to 0, right, in the sense that either the value of I can be greater than or equal to 0 at the start of the loop, or if that is not the case, then as long as the value of n is greater than or equal to 0, I do not care about what is the value of I, right, because my loop is going to guarantee that after the loop terminates, the value of I will be equal to n, and since n is greater than or equal to 0, therefore I will also be greater than or equal to 0, right. So, you can see the difference between AWP and WP, right. The weakest precondition, right, it encodes a much larger set of states than the approximate weakest precondition. But for the sake of proving this post condition, right, so if I just want to prove that I is greater than or equal to 0, I do not need the weakest precondition, right. So, I can work with just the approximate weakest precondition, right, which is just I is greater than or equal to 0. Okay. Okay. So, let's just briefly start with the VC generation. So, we want to construct this big formula, right, which we want to give off to the SAT solver, right. So, we will use this particular notation called VCQC to collect the side conditions that are needed for verifying that Q holds after the execution of C. So, recall, right, that if C is a loop, then there are some side conditions that I need to show, right. So, if C is a while loop, then I want to use the annotated loop invariant as the approximate weakest precondition, but I can only do that if the side conditions hold. So, I am going to collect this side conditions in this VCQC. Okay. So, for a while loop with an annotated loop invariant, there are two side conditions which we have already seen, right, that I should be a loop invariant, it should be an inductive loop invariant, which means I and F C I should be a valid Hort triple, and I and not F should imply Q. But of course, I mean, for this, right, I can again use my approximate weakest precondition, right. So, in order to show that I and F C I is a valid Hort triple, I can instead show, right, that the approximate weakest precondition of I comma C, I and F should imply that. So, if I and F implies AWP of I comma C, if this is true, right, then I know that the Hort triple I and F C I is valid, right. So, instead of trying to prove that I and F C I is valid, I can instead try to show that this particular formula is valid, okay. And this again means that I would have to compute the approximate weakest precondition of I with respect to the body of the loop, right, which is C. And so, I and F C I is valid if I and F implies AWP of I comma C, but this is a formula, right, now which we can construct. So, of course, C may also contain loops, right. So, C is the body of the loop, but if you have nested loops, then C itself may contain a loop, in which case it will also have its own side conditions. So, for that we also need to consider this VCIC, right. So, these are the side conditions corresponding to the body of the loop, but with the target being I, right. So, because the target set of states, right, is now I, because I want to compute the approximate weakest precondition with respect to I, right, since I is my post condition that I want to show, right. So, so let's collect all the VCs, right. So, all the side conditions. So, for a while loop there are these two side conditions, right, which is essentially I and F should imply AWP of I comma C, right. This is one side condition. The other side condition is I and not F should imply Q, and there are the side conditions corresponding to the body of the loop, right, which is VCIC, right. So, this is again recursive, right. So, if the body of the loop it contains another while loop, then this VCIC is again going to construct side conditions like this, okay. So, this is the entire set of VC, but for a while loop, right. So, the two side conditions that we have just seen, and the side and the VCs corresponding to the body of the loop, okay. Now, for the rest of the program statements, right, this VC, which is the side condition, can simply be true, right, because there are no side conditions, right. So, only for the while loop there are side conditions, but for the rest of the program there are no side conditions, right. So in particular for assignment statement, right, so VC of Q x colon equal to E will just be equal to true, right. So in general you can define it as true for all primitive program commands. So of course this is the VC, right, so I am not talking about the AWP. Okay. So what about for sequential composition? So here I want to again collect the side conditions, right, which are present in C1 and in C2. Recall that, I mean, it is possible that C1 and C2 itself may be different loops, right. So I need to collect the side conditions for C2 and I need to collect the side conditions for C1, but what is the target set of states, right. So the target set of states for C2 is Q, but for C1 it will be AWP of Q comma C, right. So it will be, so you collect the side conditions for C2 and you collect the side conditions for C1, but the target set of states will change, right. So it will be AWP of Q comma C2. So this is the formula that we get, right. So VC of Q comma C2 and VC of again some set of states with respect to C1, but that set of states is given by AWP of Q comma C2, right, because these are the set of states that I need to start from, such that on executing C2 I am guaranteed to end up in a state in Q, right. So because first I am going to execute C1, right, then I am going to, so then the AWP will guarantee that I will end up in a state which is in AWP of Q comma C2, and then if I then execute C2 I am guaranteed that I will end up in a state in Q. Similarly, what about if then else, right. So now again this C1 and C2 may contain loops, right. So I want to collect the side conditions that are present in either C1 or C2, right. So I will just correct them, right. So it will be VC of Q comma C1. So here my target is always Q, right, because no matter which branch of this while loop executes, it should be guaranteed that I will end up in a state which is in Q, right. So you will have VC of Q comma C1 and VC of Q comma C2. So this will be the side conditions for the while loop. Okay. So once we have defined the VCs, right, now we can define the AWP. So AWP is simply going to be the same as WP for every program statement except for while loops, right. For while loops we are going to use the annotated loop invariant as the AWP, and the side conditions that we have calculated, right, they will ensure that this I is actually a correct loop invariant. Okay. So putting it all together, so we'll say that this whole triple PCQ is valid if this particular formula is valid, right, which is P implies AWP of Q comma C and VC of Q comma C, right. So this AWP of Q comma C, right, so this is taking the entire program C and computing the approximate weakest precondition. For while loops, the approximate weakest precondition is the annotated loop invariant, and you also collect together all the verification conditions, right, all the side conditions which are present or which are given by this VC, right. So this so we already shown, right, how to calculate this VC QC for different kinds of program statements, right. So this side conditions will ensure that all the annotated loop invariants are actually correct, right, in the sense that they are actually inductive and they are good enough to show the post condition. Okay. Okay, so we will end here. In the next lecture, right, we will see how to or we will demonstrate this VC generation strategy, right, through an example. Okay.